Support vector machines. The basic idea of support vector machines can be illustrated with the image that we have here. And this is going to, again, look at the iris data set. So we've got Certosa and versicolor. And the data set can be linearly separated by into two classes by a straight line, right? So we can draw a line like this classifier here, this green line, and we're going to call that a vector. And it's going to be supported off of two data points, right? So that's where you get the word support vector, and then it's a machine learning approach, so a support vector machine. And that makes a pretty good classifier, right? And then that decision boundary, but the problem with that decision boundary is that they're very close to the data points, right? And so if we wanted to draw a more robust decision boundary, we might draw something like this, right? And what we're going to do with support vector machines is develop the mathematical tools that allow us to build this roadway. That's kind of what it's called, and these curves, right? So this is, you could call it like the center line, right? That's the classifier. And we want the center line to be as far away from the two items that we've been predicting. Because while these two classifiers work perfectly well, right, it's not halfway in the middle, kind of like logistic regression was. And so we want to do that. So this is what it looks like to build a street or a road in support vector machines. So that's the goal of SVMs, right? So one challenge that we have with support vector machines is that they're very sensitive to scaling. So we can go ahead and take a look at that. So here we have some on-scale data, and then here we have some scaled data. And the left plot, the vertical dimension, greatly outweighs the horizontal dimension, right? So we have a lot more data in one dimension here. So we have to apply some scaling that allows us to build a better support through these systems, right? So here you can see it like 0 to 80 and 0 to 6. And now we're going to scale it from -2 to 2, -2 to 2. And that's because the support vector machine is still going to try to optimize on the same values or the same steps, like a stochastic gradient descent. So scaling is important, just like it is in any algorithm. But we don't get away from scaling with support vector machines. All right, so just like a lot of these other methods, support vector machines can be used for a number of things, including classification and regression. But we're going to start with linear SVM classification. All right, so hard margin classification is the first thing we're going to talk about, and that demands that all instances be correctly classified without any margin violation. Right, so it's a strict approach that faces two challenges. It's only feasible if the data is completely separatable, and it's highly sensitive to outliers. So if we had SVM like this, right, and obviously this is not real, but this is again the data set, the iris data set. Here I've got an outlier, so I wouldn't be able to make a hard margin support vector machine, right? If I've got another outlier here, I'm again going to draw a classifier in between the two, but because I've got a support here, I'm not allowed to violate that support. So that's going to be called a hard margin system. And it's really not optimal for what we want to do. So to mitigate the limitations of hard margins, a more adaptable approach let's say hard margin, known as soft margin classification is employed. So let's look at soft margin. And when I want to employ soft margin classification, it might look something more like this. So now let's go and look at the versicolor and Virginsia. And so what I've got here are, I've got my decision boundary, which is the dark black line, and my dashed boundaries, which are going to be my curbs here and here. And then I have a number of soft margin, I have a number of incorrectly things that are either incorrectly classified or things that are within inside my margin. And I can set a number of parameters to help determine the width of my margin and how many things fall within that. In scikit-learn's SVM implementation, this is done by setting the parameter C. So if I set a parameter to C, that means I'm going to let a lot of things into my road, right? It's a party in the street, it's a block party. And if I set it to 1, if I set a very low number, I'm not going to constrain the optimization function very much. If I set it to 200, it says, whoa, 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 I don't want a lot of things in my street, right? Now, I might get, you'll see that I have a slightly different shape to my classifier, and my curbs are slightly different, right? But I'm a lot more stringent based on things. And, you know, depending on what your definition of correctly classified is, that's something that you can adjust, right? So if you think about C as a hyperparameter, which it absolutely is, right? And you want to regularize your model to prevent overfitting. You want to regularize your model or increase regularization. Right, which leads to a decreasing of your C value. Okay, so the smaller your C value is, the more regularized your model is. The more regularized your model is, the less likely you are to overfit. All right, so a little bit on the math before we get kicked off here. In prior parts of this text, we used theta 0 as our bias term and weights from theta 1 to theta n. That's still a very practical way to do it, but in support vector machines, the notation is typically done a little bit differently. So we want to keep with the standard notation in the field. And for that, our bias term is going to be B. And the vector frame of weights is going to be a bold W. That's my attempt to draw a bold W. So that's weights. Let's do that the same way. So a linear SVM classifier determines the class of a new instance, X, by classifying. So by classifying the decision functions or decision function of W of our weights transpose X plus B. And that is going to break apart into like weight 1 x1 plus weight n xn plus b. Right, so however many n terms that you have, that's how that will break apart. If the outcome is positive, it's predicted as a positive class. And if the outcome is negative, it's predicted as a negative class, right? Another way to write that is y hat is equal to the summation of 0 if wtx plus b is less than 0, and 1 if wtx plus b is greater than or equal to 0. Right? So we're just doing binary classification here. Now, if I were to draw this out on my 2D plane, what does this look like? So we want to draw out, let's say, draw out the decision boundary. And we can get something like this cool 3D plot here, right? And so what we have is on this kind of purple line, we have our actual space that we're trying to classify. And what we're going to do is we're going to train a decision boundary that's this grid that propagates through that space. And the line where that grid meets our space is our H0 or our center line. Now I can set the weight, so I can set the width of the street by adjusting H plus or minus 0, and that will literally mean I come out H1 on my decision boundary, and then I drop down, right? And I come out and I drop down, right? So this distance here is H minus 1, and that distance there is H plus 1. So that illustrates the decision boundaries of the system. Where the decision boundary equals 0, that's the straight line, and then plus or minus are parallel to the decision boundary, forming the margin around it, right? So training an SVM classifier involves optimizing W and B to maximize the margin while avoiding margin violations. So we need to optimize W and B to avoid margin violations if we're in a hard margin. Or we can minimize margin violations if we're in a soft margin. And soft margin is going to be much more common, right? It's very hard to actually get a system that has a pure hard margin. So typically we're going to be doing soft margins. So our goal here is to look at the weight W, right? So if we think about the fact here that our decision function is equal to W transpose X plus B, then we can think about the idea of what we're going to do with W, right? So if we half the slope of the decision boundaries where it's plus and minus 1, we double the distance to the decision boundary. So what we want to do is reduce the norm of our W to half the margin. So let's take a look at what that looks like graphically. If we were to cut down this side view, right? So if I've got W1 equals 1, I've got a boundary that goes from 1 to 1. And if I've got W1 equals 0.5, then I have a much wider boundary. So minimizing W the second norm of W, it maximizes the margin. And remember, we want as wide as margin as we can because that's going to give us a nice clear division between our two classes. So we're not trying to get a narrow margin, right? We can just draw a line and use, just use a vector based off supports like we had here for very low margins, but we want something that has a wide margin. So minimizing W, which minimizing is something that we like to do in machine learning, right? That's something that we have some skill sets for, is what we're trying to do, and that'll give us the wide margin. Okay. So to do that for a hard margin, we want to ensure that no points fall within the hard margin, right? So we want to ensure that we get a +1 for all positive training instances and a -1 or less than -1 for all negative instances, right? So we can write out that as minimize W and B of 1/2 W transpose W. So we are going to require T, which is my threshold of my instance I, multiplied by my weights transpose X of I, plus B is greater than or equal to 1 for kind of all positive cases. So the challenge here is that the W lacks differentiability at W equals 0, and this is not an easy thing to optimize, right? Because we typically want to optimize something that has smooth differentiable functions. Remember, in other algorithms, we said, hey, we can use stochastic gradient descent because there's only one global minimum. Now we have discontinuities, right? So instead of something like this, we have something, like that. We have some real sharp discontinuities. So we're going to have to use a different method for minimizing this. But right now, let's just set up the cost functions, and then we'll quickly glance at how you minimize it. We won't go into the math of it. It's actually quite complicated. But let's first put together what this cost function looks like if we have soft margins. So the cost function, if we have soft margins, is to minimize Again, we want to minimize our weights. We want to minimize our bias term. And now we also want to minimize zeta. And we're going to have 1/2 W transpose W, just like we did before, plus C times the summation of I equals 1 to M of zeta of I. And that's going to be subject to our T of I, W transpose X of I plus beta. But now that has to be greater than or equal to 1 minus the zeta of I and zeta of I needs to be greater than or equal to 0, because if it's not, then we'll just get trivial answers for I equals, right, 1, 2, 3, all the way up to M for the number of data points that we have. And zeta is our slack variable. And it quantifies the permissible margin violation for the ith instance, right? And then the hyperparameter C is what goes here, and that's what weighs everything, right? So we're going to get our margin violation, which is going to, if we have a margin violation, right, and how much that margin violation weighs, that's going to add to our cost function, right? So margin violation is going to cause this to go up. If it's a big margin violation, it causes it to go up more. And if C is high, it causes it to go up even more, right? And so the more that it's a function of how far off the margin you are, zeta, and then how strong that you turn up the C knob to constrain or to produce the weights on the back side of the soft margin, which is the exact same, again, if it wasn't clear, this part here on the hard margins is the same, and then soft margins adds this second part. Okay, how do we actually minimize this? Because it's not simple. And to minimize it, we use quadratic programming. And quadratic programming is not programming like Python or C. It's a mathematical term and is older than the programming, older in name than the programming that you use on computers. So both hard and soft margin problems are examples of convex quadratic optimization problems with linear constraints. That's kind of a quadratic programming problem. And QP, quadratic programming, involves solving optimization problems where the objective is a quadratic function and constraints are linear. So established in the 1940s and distinct from computer programming, but it's a mathematical tool for solving these quadratic problems. A variety of techniques are available through off-the-shelf solvers, all implemented in a variety of different programming languages to address the quadratic programming challenges. The general formulation for a quadratic program is as follows, and it's minimize P for 1/2 P transpose HP plus FTP subject to AP is less than or equal to B. So you have a number of matrices and vectors here. We won't go into it because it doesn't really matter here, but that's your standard quadratic programming. So the goal is to put SVM hard and soft constraints into this format and solve. And lucky for us, scikit-learn does all of that. And so that allows us to, with that knowledge, we can use a standard quadratic programming solver, can be applied to directly find the optimal SVM classifier.